Are you people familiar with LabVIEW? Do you have access to LabVIEW on your computers or not? LabVIEW is something that this book uses a lot of, and it's kind of useful for what we're doing now. Are you able to download it from our website or not? A student edition?
You have to have a license from.
Isn't the student edition available or not?
I'm looking at it from you. It's not.
All right.
It can only be installed on university-owned computers.
Wow. There goes that idea. Well, the student edition, see, it's not required, but it's got a lot of built-in things that we'd have to write scripts for in MATLAB. We can do it in MATLAB. I prefer to use what's available. His book is written with a lot of this in mind. That's the reason I'm trying to focus on. Anyway, today, let me go through this. So this is more on digital filtering and doing applications of filtering. So I gave you some homework, and one of the things. What I'm going to do is this. I'm going to go through the low pass, high pass, band pass, and band reject. And I'm going to go through it as the book discusses it and tell you, give you some tips about things. Then what I'm going to use, I'm also going to use the bilinear transform to take a function in S, an H of S that you're familiar with, and turn it into a Z transform. So you can see how you can actually take your knowledge of filtering from before and just create Z transform filters that will do the same thing. Or really difference equations that would do the same thing. And then I have a PowerPoint here that kind of it really showcases some of the things I'm trying to bring out that I won't be able to do a good job with unless I do with PowerPoint. So first of all, we're going to talk about the low-pass filters. We'll get to the book's problems too. All right, a low-pass filter in a nutshell is this. If this is omega, and this is continuous time, and this is h of omega, a low-pass filter will allow the low frequencies to go, and ideally, it will stop at some frequency, and the high frequencies won't pass. That's what a low-pass filter is. This has some value A here, and you can call that the magnitude. Now, that's the ideal. That's not something that's attainable. Normally, what we have is this. We get something like this. Get something like this. I'll put this first. Something like this, and then it will do something like that. The low-pass signal will be the majority of what's transmitted, and it will stop the higher frequency, or reduce them. But it's not like that. All right? So that's the thing to catch from. So next, low-pass filters. We talk about, and I'm using the book's examples of this, and I'm going to make comments why he chose this. So for a low-pass filter, from a digital filtering perspective, you're going to have some H of Z. And if we want a low-pass filter, the thing, you can always put a constant K there that's just a scale factor. Now you're going to have poles and zeros. I'm going to tell you right now that almost all of these are going to be conjugate pairs. And there's a reason for it that I'll get to. You're going to have poles and zeros. Well, for a low-pass filter, you want the zeros to be at a low frequency. You want these frequencies to pass. As a matter of fact, I should draw the analogy. If we have an H of omega here, this goes out to pi. Now it is symmetric, so at minus pi, you'll see the same exact thing. But for a low-pass filter, ideally you would have something like this, and this might be pi over 4. That would be the ideal. The actual obtainable one is something like this. maybe like this. It's going to look something like that. The majority, the lower frequencies, this is versus omega here, capital omega. These frequencies are going to be less really attenuated than the higher frequencies. Think of it that way. All right, so for this, what we want is the zeros here and here. And let me draw the unit or the circle here. So this is going to be the actual z plane here, and this is going to be the real part, and this will be the imaginary part. And what you always do is draw the unit circle, circle of 1 here. Now when we talk about filtering, we're always talking about replacing z in this equation with e to the j omega. So when you look at this, this is really going to be, this point right here is e to the j omega. It's the frequency of interest you're going to actually think about how the filter responds to. Now, remember before what I said, that really what we're looking at is the difference between this point and if we had, say, e to the j omega here, we have e to the j omega here, e to the j omega here. This is where the z's would normally be, right? Now, these are the poles. I'm sorry, these are the zeros. We want the zeros to be at the higher frequency if we're doing a low-pass filter. Does that make sense to everybody? We use conjugate pairs, and I'll tell you why in 1 second. So I'm going to make this like the book does. It says is e to the plus j 139 degrees and e to the minus j 139 degrees. Now those are conjugate pairs. One is just the conjugate of the other. You'll notice the magnitude is 1 of that pole, or that 0. Does everybody see that? I want an absolute 0 there. For these poles, there's more to this, but you're going to have poles for this thing to work. So for the poles, I'm going to make these poles at 1/2. Maybe I should blow that up a little. I'll tell you what, I realize I see people squinting. I'll make this larger, so there won't be a problem. So this is really going to be some constant k. And then I'm going to have e to the j omega minus e to the plus j 139 degrees. I don't know what that is in radians, but I chose degrees because the book does it this way and it's a little more obvious when I'm saying things. E to the j omega minus e to the minus j 139 degrees. The plus and minus j 139 are conjugate poles, or conjugate zeros, pardon. And down here I'm going to have e to the j omega minus, and this is going to be 1/2 e to the j 60 degrees, and e to the j omega minus 1/2 e to the minus j 60 degrees. I'll explain something about this. Well, let's take a look at this unit circle. So the poles are the zeros are plus or minus 139. So they're here. This is 1 0. And here's the next 0. This is going to be right here. And that's e to the j 139 degrees. And this is e to the j minus j 139. And then I have a pole here at 1/2 e to the j 60, and I also have a pole here at 1/2 e to the minus j 60 degrees. Now remember that when you took a look at what actually went on with these filters, what you're really doing is looking at the distance difference between this point, this point, this point, and this point, this point, and this point, and this point, and this point, right? And what you're doing is, in the book, the way he did it was, I'll try to assign these things correctly. I'm going to assign these two zeros. I'll call this L at some angle e to the j alpha 1, and this is going to call it L1, and this is L2 e to the j alpha 2. And for this, I'll call this the distance between this pole and here, this red line. I'll just label it as not L, but D e to the gamma 1, and this red line here, which is the distance between this pole and this point, as this is D1, this is D2 e to the gamma 2, and L1, yeah. Well, make a long story short, what this looks like is K, and then if I take a look at the zeros at 139 and minus 139 degrees, that's really going to be L1, L2, are the magnitude. And downstairs, it's D1, D2, and then the total angle is just E to the J, and if you take a look at this, it's going to be this angle plus this angle, whatever it is. You don't even know that. So it's that I have that as an alpha. So alpha 1 plus alpha 2 minus gamma 1 minus gamma 2. And that's just an angle you don't worry about. Don't worry about the angle on this one, because we're going to look at the magnitude of the filter. Yes, sir?
Can you do a brief overview of that, because you were standing in front of it the whole time you were drawing?
Yeah. This is basically a recreation from last time. What I'm really saying is that the distance between the pole here and the point E to the J omega is given as a magnitude and an angle. The angle I can barely show you there, but it's the angle between the horizontal plane and the actual, the angle between horizontal plane and the vector that I'm drawing there, the vector. Same here, it's the distance from here to here. Those are the poles, zeros, pardon. And it's at some angle. That angle would be here. Then on the poles, it's the distance between here to here and here to here, or L1, L2 at the given angles. Now forget about the angles for now. Don't worry about that. What you're worried about is these relative distances. Now I want you to just take a look at this one. By casual inspection, do you all see, as I skirt around here, there's going to come a point when I'm at 139 degrees where literally the distance is 0 for this one. Do you all see that?
Yes.
That is going to be something that makes it an absolute 0. That's a 0. So here, when that angle is 139 degrees, this goes to absolute 0. Do you follow me? Now think about it going in the negative direction. When you go to minus 139, it goes to absolute 0 as well. Do you all see that? So we know we have zeros out there at the higher frequencies. And I mean, really, you know, this is 180 degrees. 139 is out here. Do you follow me, class? But we've got poles at 60, plus or minus 60. Now, a pole increases the magnitude, and they're at the lower frequencies, pi over 3 radians, if you will. So what this does is, if you actually look at it in the book, the graphical drawing of this, if you plot only for positive frequencies, because the magnitude plot's always symmetric, the magnitude of h of e to the j omega, and this is capital omega, here, versus omega, and this is pi over 4, pi over 2. This is going to be 3/4 pi, and then pi here. What you're going to see, and this is in the book, is basically this. It's going to start at about 4.5 here, 4.5, and this is for k equals 1, by the way. And then it's going to come down and basically hit an absolute 0 here, just at 139, and then pop like this. It's going to go up a little bit here before pop. So you can just look at that and see that the lower frequencies are actually the ones that are passed, the higher frequencies are attenuated. Now this, I didn't tell you how to design an exact low-pass filter to get so many dB of attenuation or anything like that. I'm giving you an understanding of the filtering that occurs, all right? So remember this, wherever the poles are, that's where you want the signal to be strongest, or you want most of the signal. Wherever the zeros are, that's where you want to get rid of them. You use conjugate pairing because you're going to be going from minus pi to plus pi. All right, so you need conjugate pairs for that. Does that make sense to everybody? All right, because they have to be symmetric. All right, now, next, I want to show you something that's not in the book right in the sequence, but it should be. Yeah.
I just want to ask about the 139 degrees and the 60, that represents frequency, and that's a function.
Omega, remember, omega is an angle, right? Right. Omega is technically what? It's omega, it's cap or small omega times TS. We're going to get there in a second. So the fact is, if you're going to translate it to how the sampling affects a real-time signal, you have to understand what your sampling interval is. Yes, your TS is. Now, I'll get to that. Right? I don't want to jump too far ahead. Yes, it is a frequency in radians, right? But it's an angle as well. So try to understand that. Okay, now, I'll try to make this as clear as possible for you guys. Because what I'm gonna do is take from your background and try to show you how this can be applicable based on your knowledge of circuits and filtering. All right. Now, one of the things most of you have done are filters, and you're asked if they're high pass, low pass, band stop. So if I just had a simple situation like this, R, C, and here's my input, plus the minus, Vn, and here's my output, plus the minus V out. And I want the transfer function, h of omega. And I'll just say the transfer function is going to be V out of omega over V in of omega. Now, you've all done this, right? You basically, I know you've done it. You're not going to write differential equations and solve these things, at least you shouldn't. What you're going to do is say the one thing we need to do is put an impedance on that. And I'm going to do it in the Laplace domain. So the impedance of a capacitor is 1 over SC. Do you agree with that? Now what I'm going to say is I have an impedance, I have a net impedance right here, and I'll call that Z2. And I have an impedance here, which is just Z1, right? And I can say that this really is simply Z2 over Z1. Do you all give me that? Think about that now, right? It's actually Z2 over Z1 plus Z2, pardon me. It's simply voltage division. It's the output impedance over the output impedance and the source or the series impedance. Do you all agree with this?
Yeah.
And you've all had this. So now you put in the values for this. So I know that Z2 by inspection, this is Z2 right here, would be equal to 1 over R plus SC. It's 1 over the first impedance plus 1 over the second impedance. And if there were 3, you would take 1 over the third impedance. Do you all see what I'm doing? Now, I have that, and Z1 is just R. So when I take this, I'm going to go one step further. I'm going to divide top and bottom by Z2. So I have Z1 over Z2 plus 1. Do you all give me that? How many see what I'm doing and understand what I'm doing? I'm not trying to bore you. Is there some sort of live sporting event? I see all the laptops. Never mind. Are you with me, class? Now, I have that. Now I stick in the values. So I have 1 over, well, Z1 is just R, right? And then when I have divided by Z2, it flips this, right? So then I have 1 over R, right? Plus SC plus 1. And that's equal to what? 1 over 2 plus SRC. Take a look at that. Do you all agree with me? I let R be the same. Each R is the same value. Do you all agree? Now, what I'm going to do is divide top and bottom by RC. So now I get 1 over RC. And then I get S plus 2 over RC here. And that is H of S, right? And that parallels H of Z, but I want the transfer characteristics of this. So I don't use S, I use J omega. Don't I, class? I replace S with J omega. Everybody follow me on that? And when you take S and allow it to be J omega, then you get H of J omega equal to, matter of fact, do a magnitude of that. That's equal to 1 over RC divided by the square root here of omega squared plus 2 over RC squared. Do y'all agree with that? Class?
Why did you do the magnitude?
Because I want a magnitude plot. I don't care about phase. The only thing I care about is the magnitude of the transfer function, if it's low pass or high pass, band pass or band stop. Just forget about phase. Now if you take a look at that function, when omega is 0, what is it? When omega is 0, what do you see? It's 1 over RC divided by 2 over RC, isn't it?
Right.
Or it's 1/2, isn't it, class? And when all of a sudden omega approaches 2 over RC, then this value will become 2. Won't it, class? Or it'd be twice as much as that one, let me put it that way. And then you start getting the 3 dB point. I'll tell you one other thing that's commonly done here when filtering, when you get a filter response. You want to just have omega divided by something plus 1. That's commonly done as well. And the reason is because when omega is small, you can just look at whatever this value is and you have plus 1, so you know that that is the magnitude. Does that make sense to everybody? But regardless of what you get, when you look at this filter response here, if I call this 2 over RC here, what's going to happen is it's going to be constant, and about here, you're going to get about 3 dB roll off, and it'll start going down this way. And if you plotted 20 times the magnitude of the logarithm of h of omega on this axis versus omega on this axis, then the roll-off rate of this filter would be 20 dB per decade. And you're going to see that all the time. How many have heard of the roll-off of 20 dB per decade? Right? You got it in labs, didn't you, class? You didn't? Not yet then. You will. That's common. This is the simplest low-pass filter you can get. Well, one of the simplest, right? It's 3 elements, and the thing that's allowing the filtering is that capacitor, right? When the capacitor becomes a smaller impedance than the resistor, this starts looking like it's filtering out the actual output. Does that make sense to everybody? It's reducing the output. How many see this right here? How many have seen this type of a filter before? You saw it in Dave Irwin's course, didn't you, in circuits? Where else did you see it? In your labs, didn't you? Didn't you do a filter like that? Class, how many remember doing that in your labs? You had something like this. I'm not sure if it's that one, but it's a low-pass filter that you actually had to go ahead and do some measurements on. Now, you're familiar with that, right? So let's get a Z-transform filter based on your understanding of really analog filters. All right. So what I'm going to do here is say that my real filter response I can give is simply a constant K over, really, I can just say it's going to be S plus A. Do you all agree that this is replicating this, where K here would be 1 over RC, and A is 2 over RC? Do you all see this?
Yeah.
I'm going to just use variables. I'm not going to put in values. However, you know how to do this filter, and you sure know how to create a filter that has a certain frequency where it starts falling off at 20 dB per decade. So now follow me on this. I'm going to write it over here, and we're going to go through the process. I hope you'll appreciate it, because the book does not do this. I wish it would. So your understanding of filtering allows you to know that a transfer function of h of s is K over S plus A is a low-pass filter, right? How many see this right here? I mean, if it's asked on a test, you would say it's a low-pass. Just one look at that, you can tell, right? Now, when I take a look at this, I'm going to give some values to it. But suppose I make it 2 over S plus 2. And I chose those values out of the blue. I don't care what they are. Now, the next thing I'm going to do is this. I'm going to use the bilinear transform. Do you remember I said before, e to the minus s times nt, where t here is the sampling interval, was equal to z to the minus n. You all remember that? Right? When we took the Laplace transform and we sampled the signal and did the Laplace transform of it, we got the z transform. How many remember that at least? You don't have to remember the exactness of it, but you have to at least be familiar with the concept. So now I can say that z here is really e to the st, and t is just the sampling interval. S is that value there. S is equal to j omega plus sigma. And in this case, when we do frequency domain work, sigma is 0. Now, if you look at that, that means the log of z is equal to st And if you wanted an exact conversion, you would say S is equal to the log of Z divided by T. We don't use log of Z. We use an approximation for log of Z. The log of Z, natural log of Z, is equal to 2 times Z minus 1 over Z plus 1. And it's approximate. How many have a calculator? Who has a calculator? Raise your hand. Available. I want to prove this to you. I'm not going to prove it by the formula, but I want you to see something. Take the log, all right, of 2, give me a value of it, and then over here, take 2 over Z minus 1 over Z plus 1, and give me the value that you get here. Took log 2, do log 3, and then do log 4. So you can see what I'm telling you, it's not just something out of the blue. What do you get for log 2 here? 0.693 or something. What?
0.693.
0.693. Over here? 0.6 what? 4 something? What did you get? No, 2. Yeah, Z goes to 2, sorry.
0.6 repeating.
What did you get?
0.6 repeating.
0.666, all right? Now do log 3 over here.
1.098.
Over here, put in 3. 3 minus 1 is 2, right? 2 times 2 is 4. 3 plus 1 is 4, or 1, don't you? All right. Log 4.
1.38.
Say again?
1.386.
All right. 386. Over here. 1 point what? Say again? 1 point what? 2. All right, now, do you see that these things, for small values of Z, that they're close, very close. Do you all see that, class? With me on that? All right, important you see that. Remember that, don't forget that 2 there.
Is 2 just part of the formula, or?
Yes.
Okay.
Yes, yes. It's
Okay.
2 over Z minus 1 over Z plus 1. And that is something, I didn't work the series out on this one, but there are expansions all over the place that you can do and take just the first term. All right? Now, if you want to take a bunch of terms, you can get an exact, but this is as good as you need for most of the stuff. Because remember, our filters really have built-in adjustments. Magnitude, you put in a value K there, and if you need more attenuation, you can put in a value alpha that you can increase or decrease times the Z multipliers, but I'll get to that later. So that means this value S, and this is the bilinear transform, is really 2 over T times Z minus 1 over Z plus 1. Everybody got that? Now, we're going to take that value H of S and replace S with this. We've got a low-pass filter, right? So why burden ourselves coming up with all sorts of schemes to create them when we know what they are from analog circuits? This is the simplest one. So now I take that filter and I say H of S is going to be replaced by Z. Really, I want it to be H of Z. And I go ahead and I take that and I say it's equal to 2 over, not S, but 2 over T times Z minus 1 over Z plus 1 plus 2. You all see that? The only thing I did is replace the S with 2 over T times Z minus 1 divided by Z plus 1. Do you all see that? I've stuck in the approximation. Now I'm going to go ahead and do one other thing to make my life simple. I'm going to get rid of the 2's on top and bottom. Divide top and bottom by 2. That makes this 1. It makes this 1. And it gets rid of that. Makes it 1. Then I'm going to multiply top and bottom by T. Follow me? So now I get T over simply Z minus 1, Z plus 1 plus T. And finally, I'll multiply top and bottom by Z plus 1. And when I do that, I get t times z plus 1 over z minus 1 plus t times z plus 1. And then I can group terms, and I have t times z plus 1 divided by, it's going to be 1 plus t times z here, and then it's going to be minus the quantity one minus t. And you can do it, you could put a plus there and have plus t minus 1. It doesn't matter, but this is just a way of doing it. Now, does everybody see that right here, if I select the value for t, sampling interval, now I have an h of z, don't I? Right? And it's in a form that's very easily transferable to what? A frequency domain plot, isn't it, class? Take a look at that just for a second. If you do this, right, and you can let z be equal to e to the j omega, do you all agree with this, right? And you can take a look at this. I have 1 there, right? So when e to the j omega goes to pi, I know I have a 0, don't I, class? Right? Down here, I have a pole also, right? The pole, well, maybe not so obvious. Maybe you want everything divided by 1 plus t, and we can do that if you'd like. But how about if I give some value to t, make it easy on my life? I'll make t equal to 1, all right? Then I have h of z here equal to what? Z plus 1, right? Divided by 2z, right? 2z minus 2z, that's it, right, isn't it? Yeah, just 2z, correct, class? Now, if I have that right there, that's what? That's simply 1/2 plus 1/2 times z to the minus 1, isn't it, class? You agree? 1 over z is z to the minus 1. You agree? Then take h and let z go to e to the j omega. So I have 1/2 plus 1/2 times e to the minus j omega. Do you all see what I'm doing here? I've used, admittedly, one of the simplest possible filters, low pass filter. I wanted to get the z equivalent of it. Now, in fairness, you see this 2 here? That means the cut frequency is at omega equals 2. It starts breaking. If I'm sampling it at 1 second intervals, this is a lousy choice because I'm sampling at much too slow a rate to actually realize this filter. What you should sample at is probably something at least 1/10 of this value, probably 1/100th. Do you follow me on this? If you're going to have a filter that realizes what you want meaningfully, you can't sample at something that's close to the actual frequencies where attenuation begin. You have to sample at a much, much higher rate. And remember, that means that the sampling frequency is proportional to 2 pi over t. So you should sample at a value of t that's much, much smaller than the actual, related to the single sampling frequency or the break frequency. Now, that said, even with that, take a look at the response, what that looks like. I just want you to do it with me right here so you can see this before we move on. If I take a look at just the magnitude right here of e to the j omega, right? Just the magnitude versus omega here. What is it at 0? Just take a look. When it's 0, it is, come on, look. 1, thank you. It's 1, right? Now, go way out to pi. Do the extremes first. What is it at when all of a sudden omega is pi?
It's 0.
It's 0, yes. And what do you think it does in between? It'll do this, sort of. Actually, it's more pronounced like that. All right? It's a low-pass filter. Do you all see this, class? Now, the relationship between the frequency omega, capital omega, and small omega is this. You can write this down. Small omega is equal to times Ts, or the sampling interval, I'll call it Ts here, is equal to large omega. And that means, if you take this to the next level, that if I have Ts times 2 pi times f, that's capital omega right there. And so if you wanted to plot versus f on that axis, all right, or you wanted to do it a conversion, this would allow it in the actual frequency. If you want it in terms of f, you replace omega with this, and that would give it to you. You'd have to scale, but I mean, that would give it to you. I'm trying to show you this, how this works when they talk about the bilinear transform. Allows you to take your known filter behavior and create a Z-transform filter, all right? By the way, for this filter right here that I have, let's say this, yeah, this one right here. How do I get a difference equation that would realize that? For real times difference equation, tell me. Well, if I have h of z, let me go ahead and do it. I have h of z really is equal to what? It's equal to z, right, plus 1 over 2z. Wasn't that it before, right? Now what is that actually equal to? That's equal to y of z over x of z, right? And that means if I have 2z times y of z, that's equal to x of z times z plus 1. What do I do next if I want a difference equation? Class? Everything gets divided by z. I get rid of the z there, right? Because you know you're going to get a difference equation, and this becomes z to the minus 1. Right? Take it to the next level. Now we just take it to the end domain, right? And what do you see? I have 2 times y of n equals what? X of n, right? Plus x of n minus 1. Do you all agree with that? Class? Now take a look, it's a moving average filter. Then divide by 2. What do you notice about that? Y of n is what? Just the sum of the current and the past value of x, isn't it, class? So it is an average, it is a moving average. It's also regressive, it's an auto-regressive moving average filter, and it's the simplest one of all. It just adds 2 values, the current and past value, and divides by 2, and yet it works. And that is a low-pass filter. I want to tell you one other thing about low-pass filters. In general, you can add up any number of pass values, add and divide by 2, and that will be a low-pass filter as well. And you can do one other thing. You can put a scale factor A of n in front of each one of these, so you get a weighted moving average filter, and that will be a low-pass filter too. And by selecting the values of A of n correctly, you can get strong or you can get stronger filtering or weaker filtering. Now, I'm not going to go into all of this right now. I'm just telling you how it's done. These are used all the time. And in your Excel spreadsheets, you have these type of filters built in. They're auto-regressive moving average filters. They're used all the time. How many have used something like this before? One person. I bet you all have it, and you're not aware of it in some of the stuff. Have you ever used a data smoothing routine? Have you ever heard of that? Anybody?
I use DQs.
Well, data smoothing routines do that. A lot of times you have all sorts of things for data smoothing. Anyway, I want to get through that. Now I'm going to talk about, the next stuff is going to be, that's low pass filter, and I showed you a realization. If that's low pass filter, and I'll go back to the first example I put up there, how do you think we get a high pass filter? Just gut feel. Anyone? Swap the poles and zeros. Before, wherever the poles were, put the zeros there. Wherever the zeros were, put the poles there. That should make sense. Isn't that exactly what happens? If you go from low pass to high pass, let me just tell you this. I'm going to ask a question. There are no dumb answers. All right? Here's the input. Here's the output. This is actually the simplest, I guess. All right? By one look, is that low pass, high pass, band stop? Anybody?
Low pass.
Low pass. Why? Because the capacitor at 0 frequency looks like an open circuit. The entire signal here is actually developed right here when the frequency is 0, right? As the frequency goes to infinity, a capacitor looks like a short. It kills off the high frequencies. There is a frequency, it's called a 3 dB frequency, when this value is 3 dB, or 1 over the square root to this value, and that's an important frequency, and it's 1 over the square root of RC. Right? Without going through that, you all agree that's low pass, right?
Yes.
What is this?
High pass.
What did I do? I swapped the actual elements that created the pole zeros, right? That's the only thing I did. It's the same thing with Z transforms. You swap, if you got a low pass filter and you want a high pass, swap the actual poles and zeros. So I'm going to do that. And then I'll show you band pass and band reject. So now, next thing is going to be high pass. And I gave you the punchline on this. We're going to have an H of Z. We want a high pass filter. I tell you what, I'll go right to E to the J omega. I'm not even going to bother with Z at this point. It's going to have some constant K. Always put that in there. That's just a scale factor, nothing more. Then, what you do is this. Draw the one circle. Now, it is a high pass filter, right? That means we want to pass the higher frequencies. That means the poles you want out here. Remember before the poles were plus and minus 60 degrees and they had a value of 1/2? Does everybody remember that? Now we put them over here. We're going to have the poles at 139 and minus 139 degrees and have them with a length of 1/2. So the length of this one is going to be 1/2. Length of this one is 1/2. And these are the poles. So poles are with x's. Now I'm going to put the zeros at 60 degrees. So this is 60 degrees, and this is a 0. The way you always show a 0 is with a circle, and then at minus 60. All right? That flipped exactly what was happening before. Does everybody see that? Where the poles were, I put the zeros. Where the zeros were, I put the poles in terms of angle. So now up here, I know that I want my poles at, it's going to be at E to the J omega, which was Z, minus E to the J 60 degrees. And then it's going to be E to the J omega minus E to the minus J 60 degrees. Here it's going to be E to the J omega minus 1/2 E to the J, and that's going to be 139. And then E to the J omega minus 1/2 E to the minus J 139 degrees. And when you plot that, you will find out, in fact, you get a high pass filter. Now, here's exactly what you get. Do you remember with the low pass filter, if this is the magnitude of H of E to the J omega, the low pass filter looked like this. It kind of, and then like this, right? The high pass filter will be the exact same thing, only switched. Now you start from here and start this way. So it does this. That's what it'll look like. If this is pi, out here this is pi, this is 0, and this is 0. Now, you can almost see that what the high pass filter is, if you did this from minus pi to pi, it's symmetric. Then if you just started at minus pi and went to 0, you would have the high pass filter, what it would be like if you switch poles and zeros. How many see that right there? Are you with me? It's straightforward, but it does take a little time. Next, I have to do, I got these on PowerPoints. I got formats. I don't know if I have time to get that going. Formats. I'll just show you this. All right, this is going to be a band pass. And we can do band reject too. These are all talked about in the book. Band pass filter. Now, first draw the Z plane. Really, this is going to be the Z plane, and this is the one circle. So I have E to the J omega is the actual frequency of excitation. and I want a bandpass, H of Z. It's always K and then it's polynomial. Let me tell you something about bandpass. What you want to do, if you have a passband, is you want to put two conjugate pair poles with a value very close to 1 on the vertical axis. So make one of these poles just J.95, this is in the book, and make this one minus J.95. There's no magic about that. You could have J.99 and minus J.99, but they have to be on the axis. Do you follow me? Now, here comes the poles. It's going to be e to the j omega minus e to the minus j, or e, I'm sorry, minus 0.95 e to the minus j, or e to the plus j, excuse me, pi over 2. And then it's going to be e to the j omega minus 0.95 e to the minus j pi over 2. Remember, j pi over 2 or minus j pi over 2 are plus or minus 90 degrees. Do y'all follow me on this? Now just think about this for a second. This is the simplest possible one. And it happens, the peak of this, the passband, is going to be right at omega equals 90 degrees, pi over 2, which is halfway between 0 and pi. All right? And pi is the highest possible frequency, so it's dead center. Just watch this. As I rotate this around, right? When I'm right here, you'll notice the distance between this pole and that is a minimum, isn't it, class? That means this value is going to be very large. It's going to be 0.05, all right? And this value you don't even care about. It's going to cause this thing to have a very large value in magnitude. You all see that? By the same token, when I keep going around and I hit this pole, right, then the distance between the second one and this is very close, very small, and that's going to be a value that's very large. Do you all see this, class? And what this will look like if we take the magnitude, if this is capital omega here, and this is pi, and this is pi over 2, and this is magnitude of h of e of j omega here, you get this. Like this. And it passes a band of frequencies. And we can get to the actual value of the passband, but I'll just tell you what it normally is. You find where this, the maximum value is down by 1 over the square root of 2, or 1 over the square root of 2, so it's 70% of that value here, 70% of that value here, and this is the passband. And I'll show you how to do that. That's called a band pass. How do you think I get a band stop? Just take a guess.
Make those zeros.
That's right. Just put those up top and you have a band stop. That's it. That's exactly it. Do y'all see this, class? And these are the basic filtering. Now those filters can allow you to create a difference equation that'll do it, and it'll be a regressive moving average, but then instead of addition it's subtraction, and I'll get to that in a second. But basically all these things are implementable in very simple ways, all right, that can be done on microcontrollers or anything like that. And I know I'm out of time now. Next question is, what are you going to have on the quiz? It's going to be related to this, and it's going to be related to the homework. Yes, sir.
I don't think you ever gave back last week's quizzes.
You know what? You're right, and I've got them upstairs. If you want them, follow me. Remind me to shoot me an email or bring them. You're absolutely right, I got them upstairs.
Let's keep talking.